Alright, here's the second installment of the video series where I work out a few problems for you from your problem set. Someone mentioned that I need to add a few more jokes into the lecture, so that's what we'll start with. Today I've got a question for you. What do you call a frog without any legs? Unhoppy. Alright, let's get started. Carbon atom has a total of 6 electrons. Draw the orbital diagram for a carbon atom, then give the 4 quantum numbers for each of the 6 electrons. First thing I want to do is draw your attention to 6 electrons here. On the actual PDF file, I think I wrote 8 there because I copied and pasted from the oxygen problem, but just know that it should be 6 like it says here. So to start with, let's draw our orbital diagram, just like we did in class. I'm going to try and make it look halfway decent. There's energy. The lowest energy orbital will be 1s, and then 2s, and my 3 degenerate 2p orbitals. And that'll be enough for carbon. Carbon has 6 electrons. So I will now fill in my electrons, starting at the bottom, filling in one at a time. There's 1. There's the second with the opposite spin. 3, 4, 5, and pay attention here. Since these orbitals have the same energy, I'll follow Hund's rule and put them in opposite orbitals, or different orbitals, with the same spin. All right, there's my 6 electrons. In order to draw the orbital diagram, or excuse me, to give the 4 quantum numbers, let's make a little chart here. Let's start with electron. Alright, and let's list the quantum numbers. So we'll have an N column, an L column, M sub L, and M sub S. Okay? So the way to work this problem is you take one electron at a time, like this one here. Start at the bottom. And I'm going to call that electron that I've kind of pointed to in green there, let's see, electron number 1. Okay. Electron number 1 is in a 1s orbital. That 1 tells you that n is equal to 1. Since it's an s orbital, you know that L has to be 0. If L is 0, there is only one possible value of n sub L, and that value is 0. Since I've got it drawn spin up, I'll write my spin 1/2 for m sub s, quantum number. Alright, now the second electron will be the electron in that same orbital right there. We'll call it electron 2. Electron 2 will have an n principal quantum number of 1. Since it's still in an s orbital, L is 0. M sub L still has to be 0. That's the only value you can have for an s orbital. The only difference is my spin. Since it's pointed down, indicating my spin is -1/2. Alright, try a different color. This will be electron 3 right there. Electron 3 is no longer in a 1s orbital, but a 2s orbital, so n is 2. L, since it's an s orbital, still has to be 0. M sub L, therefore, is still 0, and +1/2. Alright, electron 4, I'm pointing to with the purple arrow. Electron 4 is in the n equals 2 level, s orbital, so L is 0. If L is 0, M sub L has to be 0, and now it's spin down, so -1/2. Got 2 more. 2 more. So for this guy, this will be electron number 5. Still at the n equals 2 level, indicated by the 2 in front of p. Since it's a p orbital, my L is changed now from 0 to 1. Since it's a p orbital, I can have m sub L values of -1, 0, and 1. I will start and I will choose to use -1 for the orbital that electron is in. It's pointed up, so I'll say +1/2. And last, but not least, this final electron, electron 6, is at the n = 2 level. It's in a p orbital, so L is 1. Now, it can't have an m sub L of -1 because it's not in the same orbital as electron number 5. So we're going to give it a value of 0. And then the spin, since it's up, is +1/2. So my p orbitals, I can kind of place these possible quantum number values below them. Right, there's a p orbital, there's a p orbital, there's a p orbital, and I had electron 5 right here, and electron 6 right here, and that's why I chose -1 and 0 for the m sub L values. All right, number 3 is an easy one. It says indicate which of the following sets of quantum numbers are unacceptable and explain why. So we just have to remember our relationships between n, L, m sub L, and m sub S. If we look at the first case, we can see right here that n is equal to 1. The 0 here tells us that L is equal to 0. The m sub L is equal to 1. And we got to stop right there. Is that even possible? If L is 0, the only value that m sub L can be for that s orbital is not 1, but 0. So that's not possible. Okay, therefore, this set of quantum numbers is not acceptable. If we check the right-hand side, n is equal to 3, that's fine. And L is equal to 0. Well, if n is 3, L can be 0, 1, or 2, so that's fine. If L is equal to 0, my m sub L has to be 0, which it is, and my spin is perfectly fine as +1/2. Number 5 says, indicate the number of unpaired electrons present in a phosphorus atom by drawing an orbital diagram. Well, I'd have to look at the periodic table and see that a phosphorus atom has, I believe it's 15 electrons. Yeah, that's right. 15 electrons. So I'll draw my orbital, or my energy diagram, excuse me, starting with the lowest energy orbital, 1s, then 2s, 2p's, 3s, 3p. And we'll stop right there. So I've got to fill in these 15 electrons in the proper order, following the rules: Aufbau principle, Pauli exclusion principle, and Hund's rule. So there's 1, 2, 3, 4, 5, 6, 7. Notice how I followed Hund's rule there. 8, 9, 10, 11, and 12, 13, 14, 15. So these 3 electrons, each in a different p orbital, are unpaired. So there are 3 unpaired electrons. All right, the last problem I'm going to do on this video is number 7. I'm going to leave 9 for you to play with and just see as far as you can go with it. Use the hints that I give you on the paper. Number 7 says write the ground state electron configuration. Ground state just means the normal for vanadium and tellurium. So in order to do this, we need our periodic table, and I'm going to circle vanadium, that's right here, and tellurium right over here. And from the atomic number for the neutral atom, we know that vanadium has 23 electrons. All right. Starting up at the top left, I go through my 1s block, and I can write 1s2, and I'm going to continue that same pattern until I actually get to vanadium. There's the n = 2 row, and that's the 2s block, 2s2. Over here I'll go through the 2p block, 2p6, dropping down, 3s2, here we go, 3p6, 4s2. So every time I count an element, every time I count a block, I'm counting an electron. And now I'm at the d orbitals. Alright, so it'll be d3. Now remember that the n block is one behind, so it's not 4d, it's 3d3. Okay, now what I could do here, let me show you this real quick. Look in green. Look at the electron configuration that I've highlighted by my green box here. 1s2, 2s2, 2p6, 3s2, 3p6. That is the electron configuration of argon. So instead of writing all that out, I could just simply put argon in brackets to indicate, or to let that represent the electron configuration up to that point. And then I would simply just finish by saying 4s2, 3d3. Now that makes writing the electron configuration for tellurium much easier because it has 52 electrons. I don't want to write all 52 electrons. So I will go and look at the noble gas on the row right above it. That's krypton. So I can write krypton indicating that I've included the electron configuration up to that point by writing krypton. So now I will now start on the actual row the tellurium's on. So that's 1, 2, 3, 4, row 5, 5s2. I'll go all the way through the D block here, 4d10, and then 5p, 1, 2, 3, 4.